Now we will have the second lecture from Katsuya Yonekura from Tohoku University. Please, Katsuya.
Okay. Thank you very much. So yesterday, I talked about the difference between SU2 and SO3. And in particular, so an important fact is that this SO3 has non-trivial first homotopy group, which is given by Day2. So please remember this fact. And also, I wanted to talk about the difference between SO3 and O3. So let me quickly explain this difference. And for my purpose, the important fact is that we can construct new topologically non-trivial bundles if we use SO3. O3. So this can be seen by just a simple example. So let's consider S1, just a circle. Then this S1 can be constructed by gluing two ends of an interval. So we consider some interval, let's say from 0 to 1. And then we can glue these two ends, and then we get S1. So this is a very simple construction of S1. And then let's consider a fiber bundle over this S1. Well, more explicitly, let's consider vector bundle. So I take some vector space. This vector space can be just considered as R3 in this case. So let's consider some vector space on which this O3 acts. And then we can construct a non-trivial fiber bundle in the following way. So first, we consider this interval times this vector space. So this is just a trivial vector bundle. This is just a direct product of this interval and this vector space. And then we take 2 points. We take two fibers. So one fiber is at the point 0, and I take the vector element of the vector space here as V0. And I also take the point 1 in this interval, and I denote the vector here as V1. Then we want to glue these two fibers. And then in this gluing, so to construct a trivial bundle, we can just set V1 equal V0. Then that is a trivial vector bundle. But we can twist the boundary condition. So in this identification between V1 and V0, we can put some group element. So I forgot to write that this G is an element of O3. So we can use a group element as a transition function in this construction of the fiber bundle. And in this way, we get some bundle. And this bundle is topologically non-trivial if the determinant of this group is -1. Then we get a topologically non-trivial bundle on S1. So this is like a Möbius strip. So it's not essential that this is SO3. We can just consider, it's not essential that this is O3. We can just consider O1. Then in the case of O1, this B is just a one-dimensional vector space. And then we can use as a transition function just let's -1. So this is just the construction of a Möbius strip. And Möbius strip is topologically non-trivial. Yeah, you can just construct Möbius strip by papers, and then you can see that it's topologically non-trivial. So we can construct a bundle in this way. And this G, this group element gives an element of pi 0. So this O3 has two connected components. One component is so this O3 has two components with determinant +1 and determinant -1. And then, so because it has two connected components, the pi 0 of this O3 is given by Z2. So the homotopy group of this O3 is again non-trivial. And I will use this fact later in my discussion of global anomalies. Okay. So the important point was that the homotopy groups of this O3 and also the first homotopy group of SO3 are non-trivial. Then by using these facts, now I want to explain some examples of global anomalies. But here, I take the traditional approach to study global anomalies or anomalies. I will discuss more systematic approach later in my lecture. But here, I just try to study the path integral measure, and I will argue that the path integral measure has some ambiguity, and that ambiguity is the anomaly. So I want to discuss anomalies which are related to pi 0 of ON and pi 1 of SON. So I have talked about O3 and SO3, but that is not essential. We can consider any N. So we can consider ON and SON. And explicitly, I consider one-dimensional system. So one dimension means that I just consider quantum mechanics. So I consider one-dimensional, maybe I should say 1 plus 0 dimensional. So I consider 1 plus 0 dimensional Majorana fermion. So Majorana means that I take these Fermi fields to be real. So I take n real Grassmann fields, and the Lagrangian is just given like this. So this is a very simple Lagrangian. Here, because I'm considering Majorana fermions, so this is, so usually here comes some phi bar, but because it is Majorana, this is just phi. So let's consider this Lagrangian. Then this theory has a ON symmetry. So ON symmetry is just described simply by rotating fermions by some orthogonal matrix. Maybe it's better to write it as G. So this G is just a element of ON. So at the classical level, this Lagrangian has obviously this symmetry described by this orthogonal group. So we want to study partition functions of this theory. And before going to the partition function, which gives some anomaly, first let me mention the most basic partition function. So the most basic partition function is the thermal partition function. So this is just a quantum mechanical system. So we take Hamiltonian of this system. Actually, the Hamiltonian of this system is actually 0, but anyway. So if we have a quantum system, then we take Hamiltonian, and we take inverse temperature, and then we take the trace of this exponential minus beta h over the Hilbert space. Then the basic fact is that this is described by the path integral on S1. And here this S1 is constructed by gluing two ends of an interval. So I consider an interval from 0 to beta. So this beta is the inverse temperature. And then I glue 0 and beta. And also, another well-known fact is that the boundary condition is anti-periodic. So fermions obey thermal boundary conditions. Which is given by this. So this Fermi field at the Euclidean time beta is equal to minus the Fermi field at 0. So this is a well-known fact. So I just use this in my discussion. So this is the most basic case of thermal partition function. And then I introduce some background fields for the global symmetry and consider some new partition functions, and then see the anomaly. First, let me discuss the anomaly which is related to pi 0 of ON. So let's take some element of ON with determinant -1. Or more explicitly, I can just take this G to be the following diagonal matrix. I can just take it to be diagonal matrix with entries -1 and +1 to +1. So let's take this explicit matrix. And then let's consider partition function which is twisted by this element. So because this theory has the ON symmetry, this ON symmetry acts on the Hilbert space. So we can include this operator, which realizes this group element, and then we can take the trace in the Hilbert space. So at least naively, we expect that we can do it. But it turns out that there is some anomaly in this quantity. So to see the anomaly, first let's notice the boundary condition. So it is described by the path integral. On S1. But now the boundary condition is twisted by the group element. So the first component of the fermion is now, so it now satisfies periodic boundary condition. So this is now plus. So the reason is that from the thermal boundary condition, we had this minus sign. But from this group element, we have another minus sign. So by taking the products of these two, we get a plus here. And other components just obey this anti-periodic thermal boundary condition. So we want to perform path integral with these boundary conditions. So to perform path integral, first we take mode expansion. So we expand these fields in terms of Fourier modes. And for psi1, there is zero mode, which I denote by this capital A. So zero mode is possible with this boundary condition. And also, there is non-zero mode. Like this. So 2 pi I tau over beta. So this tau is the coordinate of S1. Plus S. So this is the Fourier expansion with periodic boundary condition.
Probably there is n in the exponents.
And oh, thank you. Yes. Yeah, I must put n. Yes. Yes, thank you. And also, I expand other components. And so these components with j greater than or equal to 2, so they satisfy this anti-periodic boundary condition. So they don't have any zero modes. So they can be expanded in the following way. So the Fourier modes are described by 2 pi I n minus 1/2. So we get the half integer Fourier modes. So because it is half integer, there is no zero modes. So we can expand the fields in this way. And in these expansions, the important points are the following. So first, so in this case, we can easily notice that non-zero modes appear in pairs. So here the pairs means these modes with quotient B n and Cn. And they have the same and opposite eigenvalues. I mean, so this mode B has the plus eigenvalue of the Dirac operator or derivative operator acting on it, and this part has negative eigenvalue, and so the absolute value of eigenvalues are the same in these modes, and their signs are different. Anyway, so they are paired. So non-zero modes are paired. And there is a single zero mode in this setup, so which I have denoted as capital A. So this is a zero mode. And so here I don't explain the details, but it is known that this zero mode is topologically stable. So there is some kind of index theorem. So this number of zero modes, mod 2, is a topologically invariant. The number of zero modes mod 2 in this situation is called mod 2 index. And in this simple situation, you can easily check that this number of zero modes mod 2 is really topologically invariant. So I mean that, so I chose this explicit matrix, which is a diagonal matrix, but we could have chosen other matrices with the property that determinant is -1. But however, no matter what matrix we use, it turns out that the number of zero modes mod 2 is always the same. That is just determined by this determinant of the matrix. So this index, mod 2 index, is a topological invariant. And the existence, yes.
I think there is a question from Pedro.
Yes, can I ask a question?
Yes.
Oh, okay. Sorry, this is very simple, but just to see if I get things clear. You're still working with Majorana fermions, right?
Yes. Yes.
Yeah, no, but because my question is, shouldn't you demand that Bn and Cn are either the same or conjugate numbers? I'm a bit confused whether they are actually a pair of 3 degrees of freedom or if they are connected somehow, because the fermions being Majorana and being real.
Okay, so yeah, I mean, it's a bit subtle.
Maybe it's not important, so maybe you want to go on because it's not the center of your discussion, but I was just confused.
Yeah, I mean, so in Lorentz signature, it's meaningful to impose that this field is here. But if we go to Euclidean signature, it's a bit subtle to discuss whether it is a real field or imaginary. So yeah, so if we work in Lorentz signature, then so these two are complex conjugates. Then, I mean, so we can just imagine taking the real part and imaginary part of them. Then we have two variables.
Okay.
Yeah, yeah.
Okay, thanks. Sorry for the interruption.
No. Thank you for the question.
Hello.
Yes.
Can I ask a question regarding these non-zero modes? Like, I mean, what does this pair mean in the physical? I mean, in the physics context. I mean, this is kind of mode expansion. I understood that, but physically, what does it mean?
Physically,
like in a condensed matter system, like.
I mean, so I'm here. I want to discuss Euclidean passing. Maybe I'm now going to write down how they appear in the path integral. So maybe let me first write down it. So if we consider path integral, then the path integral measure is given by these coefficients. So we want to consider path integral over this Fermi field, and it is given by the product of these coefficients. So like this. So in the path integral, we integrate over these variables. So does this answer your question?
Yeah, thanks. But I have another related question. Like, if you go back to the determinant -1 condition, and can you hear me properly? Sorry, can you hear me properly?
I think, but there is some noise, but it's okay.
Okay, sorry. But so if I go to the condition determinant of G is -1, I can always choose the determinant, the elements in some other way, like mostly negative. The psi1 component is positive and things like that. So does not that put a constraint on the number of elements in the appearing in G? Because for it to be determinant -1, you must have odd number of -1s, right, in the element.
Yeah, that's right. Yes.
So does not that also change this integral measure you wrote, like in terms of Bn and Cn? I was just curious. Maybe it sounds so simple, but I can't understand.
Yeah, so in that case, I mean, so yeah, for example, we can consider family of O3 matrix like this, -1 cosine theta minus sine theta sine theta cosine theta. So we can consider this kind of matrix. And if theta equal 0, then this is -1 plus 1 plus 1. So in this case, we get this expression. And then from here, we can continuously change this theta. And then, so at theta equal pi, we get -1, -1, -1. So there are 3 minus entries. Then, so at theta equal pi, actually there is 3 zero modes. So originally these B and C are non-zero modes, but at theta equal pi, they become zero modes. So this B and C are now zero modes. So in this way, we can continuously connect from here to here.
Okay, thanks. Understood.
Yeah. But the number of zero modes, mod 2, are always conserved. Yes. Okay, so maybe I should erase it. Okay, so this is the path integral measure for the fermion. And now we consider a symmetry, which I denote by -1 to f. So let's consider this one. So this is what is called fermion parity. So this is a symmetry which just changes the sign of the fermions. So fermions goes to minus the fermion. So in theories which contain fermions, this symmetry always exists. Well, you can also consider it as a subgroup of ON in the present case. But this part always exists in any theory which contains fermions. So let's consider this fermion parity. I think there's chat. Okay. No problem. Okay, so let's consider this fermion parity. Then the path integral measure changes the sign under this transformation. The path integral measure goes to minus the path integral measure under this fermion parity transformation. And the reason is that so these non-zero modes appear in pairs. So the signs are cancelled among them. So they don't contribute. But here there is a single zero mode. So from this zero mode, by performing this transformation, we get a minus sign here.
Excuse me, Kazuya.
Yes.
Question. So I'm have difficulty in understanding that I understand that the non-zero mode appear in pair, but here this measure is an infinite product of this D. So we need to regularize this measure first, I think.
Okay, yeah, that's right.
Yeah, so I think there exists a measure regularization so that this sign doesn't change. You can take, for instance, dBn and dCn to n-1, and then the overall sign is still restored. I mean, you can regularize in some way that there's no sign change. I mean, the cutoff of this I, the superscript.
I don't think there's any regularization which
Yeah, because
without
the
this symmetry.
infinite product, so we need to regularize to discuss whether
that is correct. That is correct. Yes, I'm kind of sloppy about regularization.
yes, I think there is some intrinsic structure that we need to put into this measure, like the charge conjugation or the complex structure or something.
Yeah.
Yeah, we need to.
No, I don't think so. I think so. We only have to impose the existence of this ON symmetry, and so maybe I should say that. So there is some difficulty in regularizing this theory. So one way to regularize this kind of fermion theory is to introduce some Pauli-Vilas field.
Yeah. I understand this point, but I mean, we need to prove that under any regularization, it has this -1 change. This is our goal, but one of PV doesn't mean that. I mean, yeah, you need to prove any regularization will induce a -1 sign change rather than a spatial PV regulator.
Yeah, I mean, sorry, maybe let me say that. So I tried to say that so this Pauli-Vilas does not work in this theory because so if we try to write down some mass term in this theory,
yeah, it breaks the symmetry.
Yeah, that's right. So this Pauli-Vilas regularization does not work. So there's no regularization which preserves this ON symmetry.
Yeah. So I mean, we need to impose this charge conjugation symmetry. And
I don't think so. I think I only need this ON symmetry.
Yeah, but yeah,
I mean, so yeah, here I'm just doing some traditional discussion, and this traditional approach is not so systematic.
Okay.
So later in my lectures, I will discuss more systematic approach, and then maybe we can discuss here.
So a shorter question is that should we assume that this Dirac operator d over dt is a invertible operator? I mean, if excluding the zero modes, is it? Should we assume that it's invertible?
Invertible.
D over dt. If excluding the zero mode.
What is your motivation to ask that question?
Yeah, if we assume that it's invertible, excluding this zero mode, then we must regularize the measure so that B and C appearing symmetrically.
Yeah,
because this d over dt will transform B subspace to C subspace. So in that sense, then everything will be fine. Yeah.
Okay, so yeah, so the Dirac operator here is simply this derivative operator.
Yeah.
And this operator is kind of anti-symmetric matrix, infinite dimensional anti-symmetric matrix.
Oh, yeah. Okay, maybe we can discuss it at some point.
Yeah. So
yes, I mean there will be ample time for discussion after the lecture. I mean, if you want to come back.
Yeah. Oh, I only have 10 minutes. Yeah, let's discuss in the discussion session. So yes, anyway, so in this way, we can see the existence of anomaly. And this is very analogous to the actual anomaly. I think maybe you have learned about actual anomaly in standard textbooks. So actual anomaly can be understood by using triangle diagrams, but they can also be understood by using Fujikawa's method. And in Fujikawa's approach, the violation of actual symmetry by anomaly is described by something similar to this one. And in the case of actual anomaly, the violation which comes here is described by the Atiyah-Singer index. But here, this violation is actually described by the mod 2 index. So, so this sign factor is actually -1 to mod 2 index. So in this way, this is very similar to the case of actual anomaly. Okay, and next, I'd like to talk about an anomaly which is related to pi1 of SON. And just for simplicity, let me just take n equal 2 because nothing changes in higher n. So just take n equal 2. And I take some family of group elements parameterized by theta. So let's consider this kind of matrix. So here theta is just a parameter. And later we will smoothly change this parameter. But for the time being, let's consider this as just a constant parameter. Okay, so we consider this SON element. And in this case, it is more convenient to use complex fermions. So I just take linear combination of fermions. Then this is just a theory with Dirac-Lagrangian. So this is just psi bar dt psi. And then I consider partition function with a twist given by this element. So this partition function is again given by the path integral on S1. And the boundary condition is twisted by this group element in the following way. So this psi satisfies this boundary condition. Here, this minus sign comes from the thermal boundary condition, and this exponential I theta comes from this twist by this group element. So the boundary condition is twisted in this way, and psi is also twisted in a similar way. And under these boundary conditions, we can expand the field in terms of Fourier modes. So because of the twisted boundary condition, the mode expansion is given like this. So this is the Fourier mode expansion. So this -1/2 comes from this thermal boundary condition, and also this theta over 2 pi comes from this one. So the Fourier modes are now shifted in this way from the integers. then the path integral is given by the product of eigenvalues of the Dirac operator So in this theory, the Dirac operator is just this derivative operator. And so this partition function is given by the product of eigenvalues of the Dirac operator, which is just this quantity. Sorry. I should write it as just proportional. I'm neglecting various factors. I'm focusing on the part which depends on this parameter theta. So this is the result of the path integral. However, so there is still some sign ambiguity in this expression. So the reason is that so there are infinitely many eigenvalues which are negative, and we are taking products of these infinitely many negative eigenvalues. So sign of this expression is not determined by this formal expression. So we have to fix the sign of this expression. And for that purpose, so I require some physical condition. So I choose the sign so that the partition function is positive at theta equals 0. So this is a reasonable requirement because in the theta is 0, then this partition function is just a thermal partition function, and thermal partition function is just physically expected to be positively definite. So we impose this condition. Then we can fix the sign. So the path integral, the result of the path integral can now be written in this way. So this is manifestly positive at theta equals 0. However, let's smoothly change the parameter theta. So I change it from 0 to 2 pi. Then at theta equals 0, all the factors are positive. So I just required this condition. But at theta equals 2 pi, in this infinite product, one factor is actually negative. So that negative factor is this one, n equals 1. So this 1 minus 1/2 squared minus theta over 2 pi squared. So this factor is negative at theta equals 2 pi. And other factors are positive. So we conclude that there is some sign ambiguity in the sense that, so this path integral measure at theta equal 2 pi is actually minus the path integral measure at theta equal 0.
Sorry, can I ask, and what about the n equals 0 factor? Isn't this also negative?
Sorry. No, sorry. This product should be taken like this one. So sorry, yeah.
Okay. Thanks.
So, but also, I'm sorry that I'm running out of time, but let me conclude my lecture today. But this element, G at theta equal 2 pi, is actually the identity element of SON, because 2 pi rotation is just the identity. So, we expect that the path integral measure at theta equal 2 pi should be the same as the path integral measure at theta equal 0. But actually, we found that there's this minus sign. So this means that the path integral measure has a sign ambiguity. And so this is the anomaly, which is related to I1 of SON. So this is related to I1 of SON because this G theta, this is a function from S1 to SON. And here this S1 is parameterized by this parameter theta. So in this way, we find an anomaly associated to this one. And so I have talked about this SON, but if we consider instead its double cover spin n group, so this spin n is a double cover of this ON, then this 2 pi rotation is not the identity element of this spin group. So if we use this symmetry group, then there is no anomaly. So we can interpret either that the theory has this ON symmetry, which is anomalous, or we can interpret that the theory has a spin n symmetry, which has no anomaly. So, and either interpretation is of course okay, but for example, in the case of two-hoofed anomaly matching, it's better to have more and more anomalies, then it's more convenient to use ON. On the other hand, if we are interested in gauge theories, then there should be no anomaly, so we have to use this spin n group. Okay, I'm sorry that I ran out of time. I stopped my lecture here. Thank you very much.
Okay, thank you very much, Katsuya, for your lecture. So let's thank the speaker. Now, so I think we should stop the recording, and so we can enter into the
So how is everything at ICTP? Are people going normally to the office or?
Pretty much, I would say, in the sense that the ICTP has been open for quite some time. During the summer, it was open.
Mm-hmm.
So, I mean, of course, you have to use masks, but yeah, no, the cafeteria was open. So, yeah, things were, I would say, going quite well. Here at CISA, we had a little bit more restrictions. But still, I mean, we have been coming to the office for almost a year, so
Okay, it's nice.
it's not too bad. Not too bad. Yeah, probably it's what, traveling, which is still something that is not really happening.
Yeah,
so,
well, I will go to a in-person workshop in November in Rimberg, Munich.
Okay, interesting.
An experience for from so long.
So that will be your first workshop after the pandemic, or?
Well, there was already something at Simon's here in the US.
You mean the summer workshop or something else?
The summer workshop and also the meeting for the collaboration of categorical symmetries.
Oh, okay. Yeah. Also, you were there?
Yeah, I'm not part of the collaboration, but they invited
it was very nice
us
event.
just to attend.
Yes. Very nice.
Yeah, it was nice.
But I guess that domestic travel in the US.
Yeah, exactly. It's not the same. Like there, I went by car, so it's not like traveling. Okay.
Well, let's just wait 30 more seconds. People is connecting. Maybe we can start the recording. All right, so we can probably start. So now we'll have the second lecture from Irene Valenzuela from Harvard on aspects of the Swampland. So please.
Okay, thank you very much. Thank you for the invitation again. And thank you everyone for coming back to the second lecture. That means that the first one was not so bad. So yesterday, we dedicated a lot of time to introduce what the Swampland program is, what are the goals, which is to find what are the constraints that an effective field theory must satisfy to be consistent with a quantum gravity completion. This is a very ambitious program, right? We are trying to understand what are the constraints coming from quantum gravity. And that's why we have to use many different approaches with all the techniques that are at our disposal, either string theory, black hole physics, holography, and so on. But it's also very rewarding in the sense that if we can point out precisely what these constraints are, we can give new phenomenological implications for high energy physics. So then we started to discuss one of the most important ones, one of the most important Swampland constraints, which is the absence of global symmetries. Okay, so this is the one that is better understood. And as we said, we have already some proofs in different contexts, like perturbative string theory, or some cases in ADS-CFT. And what I did yesterday is to try to explain carefully what we mean with global symmetry, so what is the difference between global symmetry and a gauge symmetry, and also what is the motivation coming from black hole physics for the absence of all these symmetries. Now, is there any question about this before I move on? Okay, in that case, the plan for today is to continue with this topic of global symmetries. So we are going to talk about generalized global symmetries, which is this generalized notion of symmetries that has appeared in recent years, and how this connects with completeness of the charge spectrum, which was another old Swampland constraint that now we understand in correlation to the absence of global symmetries. And also the coverdisting conjecture, which will also be a generalization of the type of symmetry that is not allowed in quantum gravity. Okay, so this will be the main thing. Depending how we go in time, maybe we start already discussing the towers of states that appears at the asymptotic limits when we try to make a global symmetry very approximate. So then we will start discussing what happens if we break the symmetry a little bit, how much we can do it, and how to quantify this in terms of the weak gravity and the distance conjecture. Okay, so this is the definition of global symmetry that I gave you yesterday. Okay, it's the same slide. So we said that we need to have some local operator that is topological and that has some charged operators, okay, that transform non-trivially. Okay. Now, in order to talk about generalized global symmetry, so the first notion of a generalized symmetry comes from these P-form global symmetries, in which the only thing that we change here, sorry, I see there is a question in the chat. I have a general naive question. Is this Swampland only related to quantum gravity or happens in UV completions of any FT? Okay, this is a good question. So already in quantum field theory, there are constraints that we need to satisfy to have a quantum field theory UV completion. Okay, so for example, like we know that there are positivity bounds, right, on the higher derivative terms and so on, that in order to guarantee that the UV completion is unitary and satisfies causality and so on. So it's not something only of gravity, okay? In general, in order to have a healthy UV completion in a unitary theory, you need to satisfy additional constraints. Now, the word Swampland, when we refer to Swampland constraints, we are restricting to those constraints that are correlated to gravity, okay? So like we imagine that we already satisfy everything that we need in quantum field theory, and then we wonder what is left. Okay, so what if there are new rules, new constraints that can appear if the UV completion is in quantum gravity? Okay, so all these Swampland constraints should disappear if gravity is non-dynamical. Okay. Okay, good. And well, let me also add that it's also interesting how, I mean, people are also trying to connect all these positivity bounds and like the typical approach, you know, that you can get of bounding higher derivative terms and so on. We'll see that you can also use that in the presence of gravity to try to prove some of these Swampland conjectures, like the weak gravity, for example. Okay. Okay, so as I was saying, so the first most standard generalization comes from these P4 global symmetries, these generalized global symmetries, in which the only thing that changes is that these operators now are supported on D minus P minus 1 manifolds, because the operators that are charged under the symmetry are not point-like, but are localized on a P manifold. Okay, so the charges now are not carried by particles, as usual for the C4 global symmetries, but are carried by p-branes, okay, by extended objects, which are created by these charge operators. And the rest is the same, okay? Again, we need that this operator, the symmetry operator is topological, and that acts non-trivially, and that it satisfies some group law. So the analogous example of the shift symmetry of the axion, but for a P-form global symmetry, is to consider some gauge theory, a U1 for a P-form gauge field, such that, for example, one of the symmetries that this theory has is this P-form global symmetry, which is kind of the shift of the P-form gauge field, and you can compute as an exercise using Nether's theorem that the symmetry operator, which is going to be the integral of the exponentiation of the integral of the current is just the integration of the field strength. Okay, so this is what would be the current that you can derive from Nether's theorem. And then the charge operator, so you can do this as an exercise, it's a nice exercise, very simple. And the charged operators are like the Wilson surfaces, no? The Wilson lines. That indeed live on p-dimensional manifolds, right? And since this is a p+1, that's why this has to be integrated in a d minus p minus 1 manifold. Now, these global symmetries should be absent in quantum gravity, so we can either break them or break them or gauge them. Okay. So how this typically happens? Well, for example, we can break it by adding charged states. Okay, why is that? Well, the easy way in this case that we have a Lagrangian theory is that the current that we are talking about, right, the conservation equation for the current corresponds just to the equation of motion for the gauge field, right? Because the current is just the gauge field. So this will be different from 0, right? So we will break the symmetry, the current will not be conserved. If we have some charged matter, right? So what appears in the right-hand side is the electromagnetic current, right? So this, in general, for a p-form gauge field, is broken by p minus 1 branes. Okay, the other option is that we can gauge it. And this is done by coupling to a p+1 gauge field. Okay, so how did we do it for the axion? Then for the axion, which is a 0 form gauge field, we couple the axion, the current, to a 1 form gauge field. So now that we have a p form gauge field, we have to couple it to a p+1 form gauge field. Okay, so that we add this term in the Lagrangian. Okay, this would be, sorry, let me put the current. Okay, and this happens whenever we have like BF terms or Chern-Simon couplings in string theory. I mean, all the Chern-Simon couplings that we get are always gauging and actually breaking the symmetry of the other one. Okay, so the already Chern-Simon terms are playing the role to break. Well, are taking care of breaking these symmetries. Now, it could happen that they break it, but they break it to a discrete subgroup. And the only way then to get rid of all the symmetries is to add charged states, okay, for all the representations. So what I want to show you is how then this relates to completeness of the charge spectrum. Any question about this? Okay, so completeness of the charge spectrum, I didn't write it here, but yeah, I mean, basically it's self-explanatory in the sense that it requires that there are states with all possible charges, okay, that are consistent with Dirac quantization and so on. So you can find this statement together with the absence of global symmetries and the compactness of continuous gauge groups in the, for example, in the paper of Banks-Cyber, that I have put the reference before in some place. And you can also motivate it by black holes, but now the recent, like the most modern understanding is that this just comes from the absence of generalized global symmetries. Okay, so that, for example, if you consider, let me now focus on a 1 form gauge field. So we have the same theory that I told you before, but just the simple one. So we have Maxwell theory. And we said that the current is just given by the field strength. So here I'm talking about the electric symmetry. Okay, then we will discuss magnetic ones. The charge operators are Wilson lines, right? So they live on these lines, on these one-dimensional manifolds. Okay. And we said that this symmetry can get broken if we add charge states, if we add particles, right? How we see this in more detail? I mean, it's easy when we have the Lagrangian, we have the current, we can just study conservation of the current. But this formal list of topological operators is much more powerful because it allows you to talk about all this breaking of symmetries, even if they are discrete, even if we don't have a current because we don't have a Lagrangian. So the idea is that what's going on is that since, let me write it here, since this symmetry operator, right, is acting non-trivially on the Wilson line, okay, this is just the definition that the Wilson lines are charged under the symmetry, the operator will become non-topological, so the symmetry will be broken if the Wilson lines can end, okay, they can break. So why is this? Well, imagine that, do it a bit better. So we have this Wilson line operator, okay? And now we have this symmetry operator around it, okay? Since it's charged, if we shrink the operator, okay, since the operator is topological, we can deform it, okay? But then if we shrink it, this will give rise to the Wilson line again, just with a phase that is different from 1, okay, because we have this insertion of the operator. But if the Wilson line can break, imagine that I can break the Wilson line because I have some particles in my theory, okay, I have some local operators, then I can shrink this topological operator, right, in such a way that it disappears, I mean, becomes trivial, and then I get just the Wilson line, which would be equivalent to say that this phase is 1. But that's inconsistent with the fact that the Wilson line is charged, which means that this, in the moment in which the Wilson line can break, the operator is no longer topological. You are not allowed to deform it this way. Okay, so all this is just to tell you what is the proper, the more sharp way to talk about breaking all these symmetries, which is requiring that the operators are non-topological, which happens if these Wilson lines can end, okay, or can break. So keeping this in mind, if we add now a particle of charge n, this would mean that only Wilson lines of charge n, because they are labeled by the representations of the group, only those ones can break, which means that still I will have some Wilson lines that can end, and therefore the operators that link non-trivially will remain topological, which means that I have a CN symmetry left. And this is something which is not easy to see just from the currents, the conservation equations. Okay, so in general, if I want to break all the possible one-form global symmetries, okay, that actually belongs to the center of the gauge group, I need to have a complete spectrum. Okay, I need to add particles of charge 1 and then be able to generate multi-particle state of all possible charges so that all possible Wilson lines can end. Okay, so this is true for continuous gauge groups, okay? Any question about this? If an operator is, yes.
I have one question. Is the converse also true? If the spectrum is not complete, then you do have a global symmetry?
Yes, for continuous gauge groups, it's an if and only if. Okay. Because as we said, like if we add particles, yeah, I should have put the double arrow. If we add particles of all possible charges, then I don't have one for global symmetries. And if I don't have one for global symmetries, it's because all the operators, all these, they are called Witten operators, are non-topological, which means that they cannot break. And this is valid for continuous gauge groups if I have this isolated gauge theory that I told you about. Okay. If I start adding Chern-Simons terms and other things, then the thing becomes a bit more complicated because first it will mix electric and magnetic symmetries that I'm not considering now. And also there are other ways to break the symmetries with these Chern-Simons terms. So then it's not settled yet. Okay, but if you have a pure gauge theory with charged matter. For continuous gauge groups, this is an if and only if.
Thanks.
Okay, this is also a question in the chat. If an operator is non-topological, it means there is no symmetry, indeed. Then I think charge is not well defined. If this is correct, how do you distinguish rho equals 1 and not 1? It's just, I mean, it's like you get the result by contradiction. I mean, it's just you assume that you have some symmetry operator and that you have one Wilson line that is charged under it. So this phase rho should be different from 1. But then, since the Wilson line can break, you can see that you can deform the operator, shrink it to a point which would imply that this phase is 1, which was in contradiction to the previous assumption. So something is wrong, and what is wrong is that the operator is no longer topological. Okay, this is the way to understand it. So that symmetry is broken. Okay, another question. Considering the symmetry B minus L, if we assume this is gauged or broken, I think this would have implications as a phase force or proton decay respectively. Is this correct? Yeah. If so, how can we deal with these implications? Yeah, indeed. So B minus L is the only the possible candidate for an exact global symmetry in the standard model. And this means that according to quantum gravity, it should be either broken or gauged. So if it's gauged, it means that we have some U1 degree of freedom associated with it. Sorry. And this degree of freedom, I mean, this new U1 has not been detected yet. It's a phase force. And there are constraints on how small the gauge coupling has to be. So the constraints, the experimental constraints coming from B minus L, I think is that the gauge coupling has to be smaller than 10 to the minus 23, which is very small. So it would be a very weakly coupled gauge theory. And then you can try to construct models of how this could happen, coming from string theory and so on. And I mean, it's very interesting. There are also, there's a correlation also between this small gauge coupling and neutrino masses when you use the weak gravity conjecture. So I can talk about it maybe tomorrow if you wish. But this is one option, which is interesting for phenomenology. The other option is that it's broken. Okay, so that there's no gauge field associated to it. It's broken at some high energy scale. And then again, this is now, if it's broken, it's going to induce some operators, some higher dimensional operators that are breaking the symmetry are going to induce some proton decay. So again, you have experimental constraints about the suppression for these operators. And you can start again playing the game of what is the scale at which you should break the symmetry so that you can detect this in the near future. It's quite high, I think it's around that scale, but it's also the other possible scenario. So it depends, I mean, it depends whether we will detect like either these weakly coupled with theories or proton decay, then we can get information about whether it's broken or gauged. Okay, any other question? Okay, so what I told you here, as I said, is for continuous gauge groups, but one can do this more generally. And just so you know, for discrete and disconnected gauge groups, one can show and prove that for these pure gauge theories, this still works, but one has to add here a more general notion of symmetry, which involves non-invertible symmetries. Okay, so I'm not gonna discuss this in detail, but just for your information, in case you are interested in non-invertible symmetries, like a new notion of symmetry that has appeared very recently, that is exactly the same. Let me come back to the slide. It's the same that we had before, but with the difference that we don't require to have a group law. Okay, so the operators are not necessary, are not invertible necessarily. So this is another generalization, and it seems it's important to be able to have a one-to-one correspondence between the completeness of the charge spectrum and no global symmetries in complete generality. So this is the work in progress here. You can check if you wish. Hayden Rage et al. This is a paper that we published this year. Well, you can read more about the topic, but it's a very active topic of research now in the Swampland. Okay, and the last thing I wanted to say is that, of course, here I'm talking about the electric symmetries, but the same happened for the magnetic symmetry. The symmetry operator would be the integral of F2 instead of the Hodge dual F2. So these are surface operators. This is for Maxwell theory, okay? For the case of the U1 gauge theory. And then again, right, the conservation equation is like the of the current is the Bianchi identity. So this is different from zero. You have monopoles in your theory. Okay. And one can play the same story of having completeness of the monopoles related to the absence of all these magnetic one-for global symmetries. Okay, any question? Okay, I see. I'm still confused. It's a question. It seems to me that breakability of the line is against the assumption of topological property. Could you clarify what are the assumptions and what are the conclusions? Yeah. So the point is, I mean, here, let me write it here. What I'm saying, no one-for global symmetry, it means that there are no topological operators. And what I did is to show that this is equivalent to say that the Wilson lines can break. Okay, so this is how this is shown. So Wilson lines can end, it means that you have charged spectra. So this is equivalent to this, and that there are no topological operators, like the symmetries are broken. So in order to show this correlation, you can see that if the Wilson line can end, then the operator cannot be topological, because otherwise you could shrink it and reduce it, shrink it to a point away from the Wilson line, so that it would mean that the Wilson line is not charged under it, so you have a symmetry to start with, because there is nothing charged. So there is no topological operator in your theory under which the Wilson line is charged. Okay, so there is no symmetry left. But this is the one-to-one correspondence that one has to show. So of course you cannot have one without the other one. I mean, they come together. Okay. Is it clear now? Okay. Yeah, so this would be when I say not topological operator, I'm thinking of the symmetry operator. And here, this is the Wilson line we are talking about, okay? Okay, so let's move on. So this is all for the completeness of the spectrum. The last thing that we are going to discuss before leaving this topic of global symmetries is how to generalize this to coverdism classes. Okay, so as you can see here, like the absence of global symmetries, as I said, is at some point we'll stop calling it a conjecture in near future, I guess, because in some cases it has been really proven, but the tricky part is try to understand precisely what is the notion of global symmetry that is not allowed in quantum gravity. So everything started with just these usual ordinary symmetries, like zero-form global symmetries, and now we can see that p-form global symmetries are also not allowed. I mean, this is also captured by some of the proofs. And this relation with completeness of the spectrum suggests that non-invertible global symmetries are also not allowed. I mean, this is not captured yet by any proof, but we can go further and try, and we can generalize this to coverdism classes. Okay, so everything's about trying to determine precisely what is the notion of symmetry that should not appear, which comes is very correlated to all these developments in quantum theory that are also defining all these new notions of symmetries. So how we go to coverdism classes? Well, so I'm gonna do one example, which we can understand, and then show you how this can actually be characterized in terms of coverdism. Okay. So imagine that you have some string theory compactify on some internal manifold to give some effective field theory this is the non-compact space, D minus T. So if we have some gauge fields, we can integrate these gauge fields in some of the internal cycles, and we have some flux, okay? Some fluxes. Now, this corresponds to a global symmetry. So right now we were discussing these magnetic symmetries, right? In which the charge, okay, so this is, right? Here the symmetry operator is just exponentiation of the conserved charge. So this charge is the integral of the gauge field. So these fluxes are actually giving rise to these magnetic symmetries, which for if I am integrating, I may have a flux from a D form field strength. This corresponds to a D minus 1 form global symmetry. Okay, because it's the magnetic one. Okay. So this is what would be the charge, and the symmetry operator of this symmetry, as I said, is just IQ. Now, this global symmetry, this magnetic global symmetry, we have said that can be broken if we add states that are charged under it, which would be like monopoles. And now they are extended objects. So these monopoles are branes. Okay, so the branes are the objects that are charged under these gauge fields. So if we add D minus 1 brane, this will break the symmetry. Okay. Now, from the perspective of the lower dimensional theory, I mean, if I am compactifying on this XD manifold, this is a codimension 1 object, right? So it's a domain wall. So what is happening is that if I compactify on some internal manifold that has some flux, Q1, and another which has a flux Q2, the effective field theory that I get, right, the two effective field theories that I get can be connected by a domain wall, right? So these domain walls are changing the value of the flux. Okay, so here I have the domain wall. Okay, so the two EFTs that arise because of compactification with different values of the flux, with different fluxes, can be connected by the domain wall. Okay, so the statement that we are breaking this magnetic symmetry is equivalent to say that I have a domain wall in my effective field theory that can interpolate between the two flux vacua. Okay, this is equivalent of the physical meaning of breaking these symmetries. Okay, any question? Okay, so this is the standard thing. I mean, if you work in string theory, you are used to have always like these domain walls that come from dimensional reducing branes, and they interpolate between the different flux vacua. And that means that because of the presence of these branes and these domain walls, these magnetic symmetries are broken. Now, this is something which can be characterized with covordism group. Okay, so more generally, you could wonder, okay, if breaking these symmetries is equivalent to have a domain wall that interpolates between the different vacua that have different conserved global charges, so they are not conserved anymore because they can just change the charge from one value to the other. Is there any way to characterize this more generally? I mean, can I characterize to what extent two EFTs can be connected always by a domain wall so that I can always get rid of any possible global charge that I could have, okay, any of these topological global charges? And the answer is yes, you can do it with these covordism groups. So more generally, I mean, this is just, I give you an example associated to the gauge field, but you can construct similar examples associated to gravity and more geometrical things. But in general, topological global charges of this type can be characterized by covordism classes which is precisely the statement of whether you can have a domain wall interpolating between the two theories. Okay, so imagine that we have some compact manifold. Let's call it C, and another one, let's call it D. And I have the EFTs that arise from compactifying string theory on this manifold. Okay, so I have some EFT1 and EFT2. And I want to ask whether I can have a domain wall interpolating between both of them, which is equivalent to ask whether these two manifolds actually can be connected by a D+1 dimensional manifold, so that I can deform one into the other. And whether this can happen, whether given two compact manifolds, whether you can connect them by a higher dimensional one, has an answer in coverdising group, because if two manifolds are connected this way, in the sense that they are the boundary of another manifold of one dimension more, we say that they are in the same equivalence class of coverdising theory. Okay, so these are bordant or cobordant to each other if their union is the boundary of one dimension. Okay, so this is a mathematical definition that gives rise to an equivalence relation. Okay, you can just define this equivalence relation. So two manifolds are bordant to each other if they are in the same equivalence class if their union is the boundary of one dimension more. And this will precisely give me information of whether I can connect these two manifolds so that there is a domain wall interpolating between the two EFTs. Okay. So this forms a group. This equivalence relation can form a group, which is this coverdising group. And the different elements are like these different equivalence classes. Okay. Any question about this? So this is something that is very used also in the context of anomaly, and that I'm not sure if today I couldn't watch it, but today or tomorrow, I mean, I'm sure you will hear about it in the previous lectures. So it's also an important notion there. Okay, so why is this important for this absence of global symmetries? Well, the point is that now, thinking of all these topological global charts, sorry, I see there is a question. Should the domain wall be aligned on the diagram? Yeah, okay. I was making it like a bit thick, but it's a codimension one object. So yeah, it's like a line. Okay. Yeah, it's a codimension one. Okay. So yeah, so thinking of these topological global symmetries, Jake and Kumrun formulated this coverdising conjecture.
So
meaning that
there is one more question in the chat.
Ah, sorry. Thank you. So in what sense this is a group? What is the multiplication? Yeah, it's the union, right? So you can just so the union of the different manifolds is the multiplication in this group. So that's yeah, the two unions is still another element of the group. And the trivial element is the case in which a manifold is a boundary by itself. So I will discuss this in more detail now. So it has a very geometric interpretation. It's an abelian group, okay? Because everything commutes with each other. It doesn't matter how you join, how you produce this union. Okay, so the statement is that if we want, I mean, okay, let me say what the conjecture is. So the conjecture is that all these coverdising classes must vanish, so that this group has to be trivial, so that everything should belong to the same equivalence class, okay, to the same coverdising class, which is just the trivial one. Now, why? Because otherwise, if this was different from zero, we would have different classes no, different elements, that would give rise to conserved global charges, because it would mean that I cannot transform one into the other. I cannot have a domain wall that interpolates between one and the other. So I cannot get rid of that charge. It's like a conserved global charge in my theory, and would give rise to a d minus 1 form global symmetry. Okay, where the charges, these topological charges, would be the different classes of this coordination group. So one example is the example of magnetic symmetries for a gauge field that I gave you. This is already incorporated here, but you can have more general examples just thinking geometric terms, no, in general, like whether you can, I mean, in the end, the question is whether you can transform the form one charge into the other, like whether you can break it, because otherwise you would have EFTs that are disconnected. Okay, so the consequence of this is that all EFTs of the same dimension, okay, here we are always comparing effective field theories of the same dimension, are connected by finite energy domain walls, because everything is the same class, so everything can be connected, and this way I can get rid of all these topological charges and break all the symmetries. Any question? Okay, so the example, let me come back to the example we had of the fluxes, right? We have some internal fluxes. Now, these, since the fluxes are quantized, right? Here I have some integer, no, that they have different possibilities, which if you compute actually this coordination group, taking into account this structure, you can see that it's C, which precisely is labeled by the different integers, which corresponds to the different fluxes that you can have. Okay. So if you just have some compactification with these fluxes, it will mean that this coordination group is different from 0. So what's going on? Well, what's going on is that we need to add something else. We need to add branes to break it. So once we add branes, if we add branes, and you compute again what this coordination group, taking into account the branes, you can see that it trivializes. Okay, it's 0. So if we didn't know about the existence of branes, you could also say that, okay, because I have all these fluxes, since I need to trivialize this coordination group, I need to have branes. So it predicts like the existence of defects, no, that are breaking these symmetries. Now, in some cases are obvious, we already know, like we have branes in string theory, but other cases are not so obvious. Okay, so for example, I put here one example. If one studies the coordination group for 0 dimensions, like if I don't compactify, having a spin structure, okay, so I also have fermions, one can see that it's different from 0. And this is precisely the coordination group that matters when you study type 2 string theory in 10 dimensions. Okay, if I have type 2 string theory in 10 dimensions, you can have these non-trivial coordination groups. So you would say, okay, how string theory is getting rid of this? Well, if I am in type 2A, the defects that are trivializing this coordination group are just O8 branes. See, this is like the codimension 1 object, no, the domain wall that gets rid, oh, sorry, of this topological charge. Okay, so nice, that's fine. But in type 2B, I don't have codimension 1 branes, right? So it's not known what would be the defect, no, the charge state that is supposed to break this global symmetry. So it has been shown that it should be completely non-supersymmetric, which explains why we don't know it yet, because I mean, all the objects that we know are always BPS objects and supersymmetric objects. So this should be some domain wall interpolating actually between type 2A and type 2B. So that's, I mean, they are theories of the same dimension, so they should be able to be connected. And it's non-supersymmetric, and well, this is like an open issue in string theory, not to find out what it is. So just to say that sometimes, I mean, this coordination conjecture can be used to confirm the existence of objects that we already know, but can also be used to predict the existence of new objects if we believe that all the global symmetries will be broken. And so it predicts existence of new objects in string theory that are non-supersymmetric. Okay, and this is what people are using also to constrain the possible compactifications and also the possible gauge groups, because you can predict the existence of new defects and you can study anomaly influence on these defects and then put constraints on the possible gauge theories that can appear. So you can take a look at my lectures on the Swampland program, and there you can find a lot of references about this topic. Okay, so this is what comes together with this notion of string universality. So there's a bunch of people that are studying this in detail, like this absence of global symmetries and anomalies and so on, to try to determine what are all the possible gauge groups and theories that could appear, at least in higher dimensions, which is much easier. Okay, and then check whether just by requiring the absence of global symmetries, you can constrain what are the possible gauge theories that can appear and compare with the string theory. So compare whether everything that you can get indeed arises from a string theory, to try to determine to what extent what we obtain from a string theory is representative of everything that should be consistent with quantum gravity. Okay, so to what extent we get everything that we could get. And this is what goes under the name of string universality or string Lampos principle. Okay. Any question? Okay, so let me make a last comment about this coverdism and then we will finish this. So yeah, I was asked also how this is a group. So in order to be a group, it's also important to know that you have this trivial class. So in this case, the trivial class is when a manifold is a boundary by itself. So that if I have this compact manifold, I can shrink it to a point. Okay, so that's why it's a boundary by itself. Now, from the perspective of the effective field theory, right? What this happened is that the effective field theory is ending. So here, this domain wall corresponds to what we call an end of the war brane. Okay. I think there is a question. Does string universality imply string exclusivity? So it implies that, yeah, everything that would be consistent with quantum gravity can arise from string theory, like you can embed it in string theory. Doesn't mean that cannot arise in other ways, but then you should be able to connect it to string theory. You should be able to deform it, so that if there are other possible quantum gravities that are consistent, somehow they should be connected to string theory as well. That's what it would mean, because you have all these domain walls that interpolate between all the possibilities. So everything is connected. Can there be other domain walls that connect, for instance, Day2 and M theory? So here it's about, when we talk about these topological global charges, it's always keeping the dimension fixed. Okay, so that's, yeah, you have two compact dimensions of the same type, and then whether you can connect them can be described by this coverdism group. So in that case, Day2 and M theory are changing the dimension. So it's not described in the way I did it. Maybe we can find in a way in the future a way to do it as well, but not for at the moment. And actually, the expectation is that, okay, the idea is that when you have the same dimension, everything should be connected by these finite energy domain walls in order to get rid of all these global charges. But if we change the dimension, the expectation is that, okay, maybe we can still have these domain walls, but they are going to be at infinite distance, because since we have to change the dimension, we have to decompactify, and this implies that the domain wall will be at infinite distance, and therefore maybe it doesn't have finite energy. So that will be the difference. Okay, so yeah, so coming back this trivial class, so there is this particular class in which, indeed, since we can shrink the manifold, it means that the EFT ends. It's like the end of the war. And this is interesting because this end of the world brain, if now we can study the dynamics, and it could happen that, for example, if we break supersymmetry, it expands. So this is what gives rise to the bubble of nothing instabilities that were formulated by Witten in 95, I think. Okay, so these bubble of nothing instabilities are, again, like end of the world brains, but now imagine that I can nucleate this end of the world, like a spherical bubble, such that I have nothing inside. Okay, it's really the end of the world. So it's a hole in space-time that starts expanding if the dynamics is appropriate. Okay, so this will depend on certain energy conditions of whether it's energetically favorable to expand. But if they are satisfied, which typically happens when you break supersymmetry, then this bubble of nothing can expand and describe an instability of the vacuum. Okay, so this is interesting because if we are saying that we don't want to have all these topological global symmetries, so the covordism group should vanish, it means that everything belongs to the trivial class. So any manifold that you could construct, you should be able to shrink it to a point. Okay, so how, let me maybe emphasize, so why this bubble of nothing is a regular, smooth solution of Einstein gravity that can happen is because even if it seems very singular, because you have a hole in space-time, like an end of the world, we have this compact manifold, these internal dimensions that are shrinking to a point at the wall of the bubble. Okay, so Witten did this for this time for a circle, but you can do it more generally for a compact manifold. Okay, so if any compact manifold can be shrunk to a point, you can generate these holes in space-time that, if the dynamics is appropriate, then they will expand and describe an instability. So if everything belongs to the trivial class, everything can be shrunk to a point, so there is no topological obstruction in general to construct these instabilities. Bubbles of nothing. Okay. So this is nice because, I mean, before these bubbles of nothing were only constructed for cycles, but now we know how to do it in general, like just using this formalism of covordism. And we see that there is no topological obstruction if we don't want to have global symmetries in quantum gravity. And therefore, it's just a matter of the dynamics, whether they will really describe an instability or not. So there's also a lot of research trying to understand what are specifically the energy conditions that you need to violate or to satisfy to allow for this instability, and whether they will always disappear whenever you break supersymmetry or something like that. So this connects with another conjecture. Maybe we can discuss a little bit about this the last day, but there is this Swampland conjecture that claims that any non-SUSY vacuum should eventually decay, so that everything should be metastable at least. This is another conjecture, okay? And this was formulated without thinking of bubbles of nothing, like by different means, like actually thinking of the good gravity conjecture and so on. But now there is a new way to try to prove this conjecture by studying this bubble of nothing instabilities and try to show if, since they are all seems to be always topologically allowed, whether we can also show that they will always expand once supersymmetry is broken. Okay. Any question? Okay, so this is another example in which actually we'll see that all these Swampland statements are correlated and are related among each other. At the last day, we will keep track of all the relations that we are going to explore in these lectures to try to use them. I mean, it's interesting to explore these relations precisely, yeah, like to try to prove one conjecture coming from the other one and so on. Okay, so let's leave this bubble of nothing instabilities that will eat our universe. Let's move on let me Yeah, what I'm gonna do, let me explain what I'm gonna do tomorrow, and then we can move to the discussion, okay? So tomorrow, let me skip this. So tomorrow we are going to start discussing about what happens if we don't have exact global symmetries, but only approximate ones. Okay, so as we discussed yesterday, I mean, this is very nice because we can make very sharp statements, but actually the absence of exact global symmetries is not necessarily very useful for phenomenology. I mean, still we can use all these covariance groups to constrain the possible gauge theories and so on, but in a more naive way, I mean, since we can break the symmetries very high, this is not something that we can typically detect. So can we do better? Can we quantify how approximate the global symmetries can be? Okay, so for example, if you have some gauge field and you send it to 0, you are going to ungauge the symmetry, right? So you are going to restore some U1 global symmetry. So this restores a U1 global symmetry. And then you could wonder, okay, what happens then? I mean, in principle, that should not be allowed in quantum gravity. So I'm putting here that the gauge coupling depends on phi. So in string theory, I mean, we can change the parameters of the effective field theory, and this is equivalent to moving in the modular space or the field space of my theory, right? Like, so all the parameters are parameterized by scalar fields. So you can just think of moving in this modular space such that you approach some point in which some gauge coupling goes to 0. So the parameter space is like the modular space because they are parameterized by the vacuum expectation value of scalar fields. And then what happens, so let me tell you what happens and what we'll discuss tomorrow, and then I stop. What happens is that all these points in which you try to restore a global symmetry, they are pushed away to infinite distance in this field space. Okay, so global symmetries can only be restored at infinite distance. And tomorrow we will start with this, and we'll start discussing what is the physics in these limits when you try to approach these infinite distance limits in field space. And we'll see that what happens is that the cutoff of the effective field theory goes to 0 as you try to engineer some global symmetry. Okay, so this is what we will discuss tomorrow. We will see how the cutoff of the effective field theory goes to 0 as the gauge couplings goes to 0, or as you approach more generally this infinite distance space, and what is the physics associated to it, which will be described by the weak gravity conjecture and the distance conjecture. Okay. So we'll start with this tomorrow more slowly, and then come to these more interesting, more phenomenologically interesting conjectures, which are the weak gravity and the distance. Okay, so let me then stop here. Thank you for your attention again, and let's see if there are further questions.
Okay, thank you very much, Irene, for this very nice lecture. So let's thank Irene. So now we can stop the recording. We go into a more informal environment. Let's see if I can do that. Okay, should be stopped. So so now we can start with the. Okay, is the recording stopped? Can the CTS confirm? Okay, it should be stopped. So let's go with the discussion session.
Hi, so I wanted to understand cobordism better. So could you give like a simple example of a cobordism group maybe in low dimensions, like where the boundary is, I don't know, it's some lower dimensional manifold.
Yeah, so for example, here, I mean, the easiest one is the circle, right?
Yeah.
So if you have S1, right, some circle, and you study, yeah, what is omega 1, because it's a one-dimensional manifold. So here you can see that this is C2, which means there are two possibilities. Well, let me say, so first, if I don't have fermions, this is just 0, in the sense that the circle, you can always shrink it to a point, because you can always fill the circle. No, it's like the circle can be the boundary of this cigar, and therefore the cobordism group vanishes, okay, because the circle is a boundary by itself.
Okay.
Now, if you put, for example, fermions, then you have to study the cobordism group with a spin structure. It's like something like stranger theory. And then you can see that the result is C2, because there are two possibilities, whether the fermions have periodic or antiperiodic boundary conditions in the circle. And then it's the same, like if they have antiperiodic boundary conditions, then it's the trivial class. And then again, you have this cigar, which would be the null bordism, like the cobordism manifold that is able to shrink the circle to a point. This is like the easy example because it's just one dimensional, and it's the easy one.
But don't we need two boundary manifolds? I mean, okay,
So
there is trivial one where it's cobordant to itself, but in general, we need two boundaries, no?
So in general, let's see. So the point is that if you have two manifolds which are...
You should definitely feel entitled just to unmute yourself and speak up if at any point anything I say is unclear, or if you have any comments or anything like that. So yesterday, based on an observation involving Euclidean wormholes, we speculated that a more correct version, or perhaps we should say more general version, of the ADS-CFT correspondence is one that relates a theory of gravity in anti-de Sitter space, that is to say, a theory of fluctuating metrics in asymptotically anti-de Sitter space, to a probability distribution. Okay, it looks like my tablet has frozen actually. Can you not see what I'm writing here? Okay.
Yeah.
Can you hear me okay?
Yeah, I can hear you. It stopped
Okay.
at the ADS-CFT.
Okay, give me one. This happened to me yesterday where suddenly my tablet got kicked off of the network. Yeah, hang on just 1 second. I'm going to try and reconnect. Sure. But you guys can hear me okay? Okay, well, what
sound is great.
Yeah, it's weird. My tablet just spontaneously disconnected from the internet. Okay, well, I don't know, talk amongst yourselves. Francesco, do you know any good jokes to keep the audience entertained?
Not a good entertainer, unfortunately.
Do I know any good jokes? There were two cannibals eating a clown. One of them said, "Does this taste funny?" That's my favorite joke. Everyone's heard that one already. Okay, I'm sorry, my tablet seems to be being very slow this morning. Okay, I apologize for this.
No problem.
everyone can go get a cup of coffee. Hopefully this will be just a second. Okay, I might have to try and restart.
Okay.
Why don't I do that? And I'll talk in words while my computer restarts. So yesterday, we speculated that there was a more correct version of the ADS-CFT correspondence, where instead of a theory of gravity in asymptotic anti-de Sitter space being related to a particular conformal field theory, we instead speculated that it was related to a probability distribution over the space of conformal field theories. And this way of thinking about the ADS-CFT correspondence, in some sense, just generalizes our more traditional version of ADS-CFT, because you could always take a kind of trivial probability distribution where you just have a delta function on the space of conformal field theories. So, for example, in this picture, n equals 4 Super-Yang-Mills theory is still dual to type 2B string theory on ADS5 times S5. The only difference is now we're allowing ourselves to think about more general probability distributions aside from just the delta function distribution. So, for example, what I'm going to be talking about today is I'm going to introduce two different models for this averaged holographic duality. So in particular, I'll introduce a theory of gravity in 2 dimensions, which is going to be related to an average over one-dimensional quantum mechanical systems. So in particular, this is a theory of gravity, JT gravity, which is going to be described by an integral over a space of Hermitian matrices, each of which are interpreted as the Hamiltonians of some underlying quantum mechanical system. And the other model that I'll introduce and will sort of occupy most of our attention for the next 2 lectures on Wednesday and Thursday is a model where we integrate over a full space of conformal field theories. Very simple conformal field theories, but non-trivial conformal field theories nonetheless. And we interpret this as a theory of gravity in anti-de Sitter space. So in particular, in this setup, we'll be talking about a theory of 2-dimensional conformal field theories, and we'll consider a family of such CFTs with a finite dimensional moduli space. We'll average over that space of CFTs and argue that it's related to a sort of 3-dimensional theory of gravity. Okay. And now it looks like my tablet has healed itself. So let's see if this works. Sorry, we run into an issue. Okay. You never like it when your tablet. Yes. Oh, please. That's a great thing to do.
Is the distribution intrinsic to the theory, or we just finding some examples?
Good. So I think in this picture that I'm trying to advocate, a theory of gravity specifies a probability distribution on the space of conformal field theories. So for example, in the case of JT gravity, it turns out there's an incredibly specific probability distribution on the space of Hermitian matrices that gives you an answer that is equal to the JT gravity partition function. Similarly, in the Narayne example, there is a very specific probability distribution on the space of conformal field theories that gives me an answer that looks like a theory of gravity. Okay. Sorry, I just need to remember the meeting password. In particular, it is presumably the case that you could take one space of conformal field theories and then consider multiple different possible probability distributions on this space of conformal field theories, each one of which would correspond to a different theory of gravity. Good. Let's try this again. Any other questions while I get this all set up?
Can I ask a question regarding this probability distribution thing? So you say that each CFT is corresponds to a particular theory in JT gravity kind of thing. But is it what guarantees that these are one-to-one? I mean, is it possible to have like more than one CFTs correspond to the same theory of gravity and vice versa?
Well, I mean, what I would say is that, so as far as we understand, one probability distribution on the space of conformal field theories corresponds to a theory of gravity. Of course, the usual understanding of ADS-CFT accommodates this. Different delta function distributions on the space of conformal field theories correspond to different, string theory compactifications down to ADS, for example. And I see no need to have a different picture once we're talking about more general probability distributions. In any case, maybe now that my tablet is working again, I can just try and shift gears and proceed with the lecture as I was planning. But again, oh, that's not good. Okay, my tablet is suddenly disconnected again. Okay, I'm sorry about this. It's a Zoom problem. Zoom is just disconnecting.
So can I continue?
Yeah, please continue with your question.
So
yes.
you said that there is no need. I mean, is this something because this is kind of more ambitious project to pursue, or why there is no need? I mean, what will be? I mean, that will be nice, right? If we have like two CFTs dual to one gravity. I mean, it's. I mean, no. Why
You
there
want
is no
two
need?
CF? I'm not quite sure what you're asking.
Yeah. I mean, why there is no need to have two CFTs dual to one gravity theory? I mean,
what do you mean? Why is there no need to have two CFTs dual to one gravity theory?
You told me that. I mean, in view of the usual ADS-CFT duality, there is no need to have this kind of correspondence. But what I found that, I mean, if it is possible, then we can group the universal class of CFTs kind of. I mean, more general universal class of CFTs correspond to one gravity theory. That will be nice, right?
I guess I'm not quite sure I understand your question.
Okay, so what I was asking that, I mean, the probability distribution of two CFTs, can it correspond to one gravity theory or vice versa? But your reply was that in view of the usual approaches to ADS-CFT, that is not usually the case, right?
Okay, do you mind give me a minute to try and get my tablet connected? It's hard for me to both pay attention to you and to try and fix my tablet.
Okay, I'm sorry.
So yeah. Okay. I guess I apologize for this. I keep getting messages that Zoom experiences an unknown error. Okay, sorry. I taught 2 classes so far using exactly this setup and given hundreds of lectures and never had this problem before. I think it's a Zoom problem. Sorry, this is not a particularly fascinating thing for everyone to be watching. I think it is a problem with the internet on my tablet. It seems to just keep getting disconnected. Okay, we'll give this one more try, and if that doesn't work, we'll go to plan B. I can always, you know, I have a million different, I have lots of different slides I can pop up so that we have something to look at while we're doing this. But this is a surprise. I mean, I think over the last year, I must have given 100 different lectures, seminars, and so forth using this tablet and never had this problem.
There is always a first time.
There's always a first time. That's right. Okay. And I didn't mean to cut off discussion. It's just difficult for me to both try simultaneously connect my laptop and pay attention to questions.
Maybe can I ask you a very simple question?
Sure.
Which will not distract you too much. Yes.
Yeah.
I just wanted to ask you, I'm not too much expert in ADS-CFT. So is there a sharp ADS-CFT correspondence where the CFT has a multiple disconnected phase space, space-time, but a sharp one, which you can reproduce starting from deep brains?
So I'm not quite sure. What do you mean? So what is the criteria that you would like for your
I would like
theory?
to know if there is an ADS-CFT correspondence which is based on a string construction like n equal to 4, where the CFT is not defined on RD or whatever space, but it's somehow defined in a multiple disconnected components. If you wish, we have a couple of CFTs, in some sense.
One can always, for a given CFT, study that CFT on some disconnected space-time. So here we have to be careful about whether we're talking in Euclidean signature or Lorentzian signature. And the idea is that in Lorentzian signature, as we maybe mentioned at the end last time, or perhaps it was during the question session, in Lorentzian signature, you know, black hole spacetimes, eternal black hole spacetimes have multiple boundaries. And there's nothing particularly complicated about that. You know, they're ubiquitous. They would appear in almost any, you know, gravitational theory, sufficiently complicated gravitational theory. On the other hand, if you're talking about in Euclidean signature, one could always just define the CFT partition function in Euclidean signature. And there's nothing wrong with considering the partition function on a disconnected surface or on a surface that has multiple disconnected components. So for example, n equals 4 Yang-Mills, there's no reason why you couldn't study n equals 4 Yang-Mills on, you know, 4 manifolds that are disconnected. The problem is that, you know, one of the basic principles of conformal field theory, it's almost an axiom of conformal field theory, is that the partition function factorizes when you do that. And so presumably, if you were to study type 2B string theory on a family of, you know, on a space-time in Euclidean signature that has multiple disconnected boundaries, there would be some reason why in, you know, the full type 2 string theory calculation, you wouldn't get a contribution from spacetimes that connect multiple boundaries. The problem is that nobody knows how this works.
Yeah, thanks. Sorry, my question was on the explicit construction. So suppose you take n equal to 4 on any manifold you like with multiple with 2 disconnected components. My question is, do we have a type 2B background which we understand to be the dual of this configuration from a stringy point of view, like on ADS5 times S5 at the same level?
No, not as far as I know. Yeah. So for example, yeah, I apologize. Sorry for this. You know, my tablet is just, okay, now it says it's connecting. Okay, I'm sorry about this. It's hard for me to both answer questions and try and fix my computer at the same time. All right. I'm giving up on my tablet.
Okay, give me up. It doesn't work.
Yeah, it's just been, I mean, it's been 15 minutes now of spinning wheels. I've already restarted it. Doesn't seem to help. Instead, what I would like to do, if that's okay with everyone, is pull up a set of slides.
Sure.
These are
Somebody
not,
was proposing to use the blackboard behind you, but I don't know if that is a good
I don't know if it's
idea.
gonna, can you see the blackboard behind me okay? I would also need to dig up some pens.
Yeah, I
I
don't
mean,
know.
I do have,
probably not. It probably is not clear. Yeah.
you know, I do have my kid's iPad is kicking around somewhere. I could try and find that. That would be the most fun.
No, but I mean, if you have slides, it's perfectly fine. Absolutely.
You know what? Okay. Yeah, I'm still getting an unknown error code. Yeah, I'm getting an unknown error code on Zoom. You know what? Why don't I try? Can we all take a 5-minute coffee break while I go try and find my my kid's iPad and see if I can get that hooked up? I'm sorry about this, everyone. You know, I'll personally refund your admission fees. I hope they didn't charge any admission fees. Okay, I'll be right back in 2 seconds.
All right.
Sorry about this. Unfortunately, it still doesn't seem, I can't seem to join the Zoom meeting here.
I see.
Alex, what error are you getting when you try to join with a new device?
Okay. It says, I think there's a firewall or proxy setting that's not letting any of my devices join on Zoom. So when I try with my tablet, I'm getting an unknown error. When I try with my iPad, I'm getting, make sure your connection to Zoom is not blocked by a firewall or proxy.
I wonder if our ICTS people, it might be.
Yeah. Is it possible that
Massimo, are you there?
Try again.
I'm here.
Massimo, so the speaker, Alex Maloney, he's being blocked by a firewall in connecting now.
Yeah.
His previous device was not working, and now when he found a different device, he can't connect it. So I think there might be an automatic blocking of his devices to our network.
Yeah.
I mean, to the Zoom call somehow.
Zoom is not.
No, it's working fine on my computer, but whenever I try and connect either my Windows tablet or my iPad, I'm getting messages that it is blocked by a proxy or a firewall.
Are you using the ID or the registration link?
I'm using the meeting ID.
Just meeting ID and password.
Mm-hmm.
Meeting ID and password.
Yes. Just the meeting ID and password. Yeah, it says, okay.
There is no reason that
I'll try again.
Second device cannot, because you are not, there was no registering for this meeting, is correct?
No, there was a registration.
There is a registration. Are you using the same email for both?
I mean, I'm just trying to join the meeting directly.
No, Massimo, there was a registration because we're using UNESCO Zoom, but once you have the Zoom credentials, I think anyone can log in with it, in theory.
Let me check. It could be that because this is one UNESCO Zoom and it's not our usual Zoom.
Yeah.
Let me check if there is, maybe it could be that you have to be unique. Can you register with another email also to have double?
Well, there's no, I don't understand, there's, as far as I understand.
Excuse me, can you repeat?
You don't need the email to.
It doesn't use an email address.
To log in.
I just get login credentials.
You didn't have the registration to Zoom. Just let me check. Copy invitation. No, there was an invitation. The registration link. There was a registration link for Zoom.
Yeah.
I can enter in edit because we are joining the room.
But is there a prop? Is it not letting me use the same link to sign in from two devices? Is that the problem? I think that might be the problem.
That could be the problem. Yes. This is
not so I see. So it doesn't want me to log in simultaneously from a tablet and from the computer that I'm using.
Yes.
That doesn't make sense because Irene was using two devices.
Yeah. And I was doing this yesterday and it worked fine.
Yeah.
But yesterday you used both tablet and the computer.
Yeah.
Yeah.
So I didn't change any preferences or details on the meeting, so it should be like yesterday.
Yeah, I'm not quite sure what to say. I'm neither able to join through the iPad or through my tablet.
Shall we go with plan C, Alex?
Yeah, I'm going to try this one more time. Sorry about this.
The only difference to me seems like before you joined, like before the recording started, and now it's after. Maybe this is somehow related.
I paused the recording anyway.
Okay, now I'm getting, all right, let's give this a try. Okay.
You enter with another device?
Yep, now it's letting me on.
Okay, that's good. Which nick you use on the second device?
I just put the name Alex.
Alex.
Let's see if that works. It says waiting.
Let me check.
Ah.
No, there is no waiting room.
It says connecting.
Okay. I
Got
give you
it.
the
Okay.
code to
All
the
right.
other device. Maybe it can help. Let's see.
All right.
Try
I
and
seem to
display.
be, okay, here I am. Okay.
It's okay.
Now I just need a notepad. So anyone who uses iPads, there must be a notepad application.
If there's nothing installed, you should be able to just use the notes app. That should allow you to write on it.
I can use one.
Just the generic Apple Notes app. It should allow for handwriting. Like it's not amazing, but
it's not great. Okay,
yeah.
That's fine.
But
we'll just go ahead and
most
use
of the
that.
other ones are paid for.
Yeah. Okay. You guys can see my iPad. Great. Good. You guys can see this okay?
Not yet. There might be a long delay.
Yeah.
Good. Okay, great. Okay. Okay. Okay, this will be fun. Okay. So where were we? Let's see. Can you read this okay? So we speculated. Okay, broadcast to Zoom has stopped due to attempted to start invalid broadcast session. Uh-oh.
Yeah, we don't see.
So you guys can't see anything.
No, it's frozen.
Yeah, I got kicked off Zoom again. It's possible that it's something to do with my wireless network here, but I'm just surprised because now it seems to be working again.
Again, these kind of issues so far. Now we can see your tablet, iPad, desktop.
Okay, good. Now it seems to be working. You guys can see this okay. Okay, we'll see how this goes. Okay, it's an adventure. We're all in this together. Okay, good. So we speculated, and let me know if this thing crashes at some point, or if you can stop, if you can't hear me anymore. We'll see how this goes. So we speculated that a more correct version, or we might want to say more complete version of the ADS CFT correspondence, is one that relates a theory of gravity in asymptotically ADS space to some probability distribution over the space of conformal field theories. So in this picture, a quote unquote fancy theory of gravity. And this would be one that is completely UV complete. And in particular, a theory of gravity where we can completely understand the microscopic physics of black holes. That should correspond to some sort of delta function distribution on the space of CFTs, where this theory of gravity is dual to an exact conformal field theory. That is to say, a single conformal field theory. On the other hand, the problem with such fancy theories of gravity is that they are nearly impossible to study precisely in the bulk. And so instead, if one studies a simple theory of gravity, perhaps such as quantum general relativity, this would correspond to some non-trivial probability distribution over many conformal field theories. And this has the advantage that it is not a complete UV complete theory. So it's not UV complete. There is no sort of complete understanding of black hole microphysics. But nevertheless, we can understand, for example, the path integral theory of the theory exactly.
So can I ask? I guess we lost the
Please, 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 please.
So this non-UV completeness and not complete understanding of black hole microphysics, how do you see this in the CFT then? Because in principle, okay, you need to take a distribution now, but in principle, I would imagine I would be able to compute anything in the CFTs, right?
Good. So, good question. So the point is that, one of the characteristic features, and this is something that we'll get into in a minute, one of the characteristic features of these quote unquote simple theories of gravity is that they don't have a discrete spectrum. So for example, physics in ADS is like physics in a box. In particular, the spectrum of the theory, including the spectrum of black holes, is discrete. And so, for example, if you want a picture of a black hole in anti-de Sitter space, you should think of it as a black hole in a box whose size is the ADS radius. And this black hole is in equilibrium with its own Hawking radiation. So you sort of think of it as being in equilibrium with its Hawking radiation. So in any complete theory of quantum gravity in anti-de Sitter space, you would expect a discrete spectrum of states. And indeed, in any conformal field theory, at least in any standard compact conformal field theory, the spectrum is going to be discrete. So in particular, the spectrum of operators, which is the same as the spectrum of states because of the state operator correspondence, is going to be a discrete spectrum. Okay. So in any sort of single compact conformal field theory, you're going to get a discrete spectrum. But all of the attempts to obtain a discrete spectrum directly from a gravitational path integral seem to have failed. With a few very specific exceptions that we'll get to in a minute. Okay. And all good things must come to an end. And the screen now has disappeared again. And I seem to have gotten kicked out of this Zoom session. Okay. I am not quite sure what to do here.
We could.
I don't know if this is a problem with my internet here, with the devices that I'm trying, with the way that Zoom is configured at ICTP, or what. So none of the other speakers have had this issue, as far as I understand. Is that correct?
Yeah.
Okay.
I mean, also in your case yesterday was fine. So this is quite.
Yeah.
Strange.
I mean, I can just try and reconnect because that was working for a minute.
Otherwise, I mean, other possible options could be either if you have some slides, we could go through them, or we could do some discussion in which maybe you introduce some ideas without formulae and.
Yeah, I mean, I suspect. I mean. Okay, I'm sharing my screen again. I strongly suspect it's going to work for a few minutes and then stop again. I have a sneaking suspicion it might have something to do with my internet here. Where was the notes application? I mean, what we could do is, this appears to be working right now. So why don't I proceed?
Go ahead. Yeah.
And then we'll see how it goes. Okay.
Go ahead. Yeah.
Because what else can you do in life, right? Okay. So, yeah, I don't want to spend too much more time mucking around with tablets and stuff like that. So let's just talk physics. And if it stops working, I'll just pull up some slides from a talk that I gave. And then we can have a discussion. And then we'll get this all sorted out for our lecture tomorrow. So, but what I really want to talk about from the physics point of view is that there is a real precedent for this. In condensed matter physics, when we study disordered systems. Okay. And it seems to have frozen again. Gosh. You guys can't see this. Okay, now it seems to be continuing. Okay, it's slow. It's slow. It's slow. You know, I wonder, okay, I'm going to stop talking about this, but I suspect it's the fact that it's something to do with my internet at home, which is unfortunate. Okay. In any case, when we study the physics of disordered systems in a condensed matter setting, what are we doing? Well, we're typically studying a very complicated system. So for example, you could imagine studying something like the Ising model, where we have a bunch of spins that are interacting pairwise. Okay. So here I've written down the Hamiltonian of the Ising model, where we have a bunch of spins that are interacting via some couplings that I've called Jij here. Now, in the traditional Ising model, these Jijs would all just be some constant. This is an exactly solvable system that you all probably know quite well. But if we were studying a more complicated system, then those Jijs could be complicated numbers that are essentially random. And if these Jijs are some very complicated numbers, then this would be a very difficult problem to solve exactly. And in particular, if the Jijs are sufficiently complicated, this might be spin glass, for example. In that case, this would be described by the famous Sherrington-Kirkpatrick model or the Edwards-Anderson model. Okay, and now my tablet has disappeared again. But in that case, just to complete the thought, in that case, the individual Hamiltonian that I wrote down just a second ago is very difficult to study exactly. And so the approach that condensed matter theorists take is, rather than trying to study an individual Hamiltonian with very complicated coupling constants that are essentially random, you treat those coupling constants as stochastic variables, as random variables. And you consider the ensemble of Hamiltonians where those coupling constants are all pulled from some statistical distribution. And the remarkable thing is that these ensemble averaged theories are often much easier to study, and in some cases are, in a sense, exactly solvable, even though the individual Hamiltonians that make up the ensemble are almost impossible to study. Okay, some people are suggesting on the chat window that I use the whiteboard. Unfortunately, I don't have any markers for the whiteboard, so that's not going to work. Just to complete the thought, however, in this analogy, what we're imagining is that a theory of gravity, a simple theory of gravity described by a path integral, is something much like the averaged theory that is used to study the Sherrington-Kirkpatrick model, whereas the UV complete theories of gravity are the individual instances of the ensemble, the individual Hamiltonians, which have some very complicated coupling constants. And these are the things that make up the ensemble. These are the things like n=4 super Yang-Mills theory. And so, for example, the fact, if you took a spin glass, that's an actual chunk of material, okay, which has got a Hamiltonian and a Hilbert space and all of that good stuff. And it has a discrete spectrum. It has a discrete spectrum of states, but just a spectrum that's very, very hard to study. And so if you want to instead go to the more coarse, ensemble averaged description of the system, then that's a description where you sacrifice something. You sacrifice an exact knowledge of the microstates of the system. You sacrifice a discrete spectrum and all of that stuff. But the reward that you get for making that sacrifice is that you then get a system which is exactly solvable. Okay, you get a system where you can, compute coarse features of things like the density of states or the statistics on the density of states exactly. And so the way that I think about these ensemble averaged theories is that they are like the post-averaged version of the Sherrington-Kirkpatrick model or the Edwards-Anderson model. Okay. And so what we're doing here is we're doing essentially a conformal field theory approach, a version of the same physics of disordered systems that condensed matter theorists study. That, for example, it's a good week to talk about spin glasses, right? Because we have Parisi giving a colloquium at the end of the week, right? And so a lot of the inspiration, I think, for this particular point of view of the ADS-CFT correspondence comes from this condensed matter analogy. So we have a couple of different ways that we could proceed. Let me ask you the following question. How readable is this? This is not very readable. Because I do have written notes. Is that readable at all? Is that backwards? It looks backwards to me.
It's not backwards. That is, if you hold it close, it is actually readable. Yeah.
It is actually readable. Okay. I mean, this is like, I don't know. Back in the olden days when people gave lectures on blackboards, you didn't have to deal with things like Zoom crashing in the middle of your seminar. So it is readable. Okay. So maybe what I would suggest is I could proceed. Yeah. I mean, is this insane? It might be insane, but that doesn't mean it's the wrong thing to do. What I could just do is just read through some of these things and then take breaks to answer some questions. Does that sound reasonable? Someone suggests I can turn off the camera to free the Wi-Fi line. It's possible. I suspect that's not going to help. Okay, I could scan them and post them on the Slack. I was planning on doing that anyway. Okay.
But maybe at this point you can tell us in Word, and then if there is
what
a
don't I tell you?
formula,
I mean,
can,
we've spent 50. It's been 50.
us,
It's been 50 minutes. It's been 50 minutes. I don't want to continue. I don't want to continue this process indefinitely. So maybe what I would suggest is that we turn the rest of this meeting today into a question and answer session, and then we'll try very hard. What I'm gonna do is go to my office and try and give my lecture tomorrow from my office, where hopefully all of these problems will be resolved. But I would suggest that we just turn the rest of this lecture today into a question and answer session, if that's okay. Sorry again about this. I mean, I swear I've taught 3 classes and given God knows how many seminars using exactly this setup, and this is the first time it's happened. Good.
So
please,
to get started.
please. Yeah. Okay. Now I can answer questions because I'm going to be devoting my full attention instead of trying to fuck around with my tablet at the same time. Okay.
And maybe we can stop the recording at this point, since it's going to be a discussion session.
I mean, if the recording of this vanished down the memory hole and was never posted on the internet, I would not necessarily object. Okay, there was a question.
Can I go, or is it?
Yeah. Please, please.
Okay. So the goal is not then now. So the goal is not now to start again really understanding really the microscopic states of this black hole physics. It's more to have some effective description, find the distribution which resembles what we know should happen in black holes.
Yeah. I mean, I think the thing that is remarkable about this set of examples that we're considering here is that they reproduce a hell of a lot of the microstructure of black holes, even though they don't reproduce the discreteness itself. And this is a point that I think was probably originally made by Schenker and collaborators in their paper on black holes and random matrices, which is that even though when we talk about trying to reproduce the microphysics of black holes, the gold standard would be to reproduce the exact spectrum of states, a discrete spectrum of states. But that is a very tall order. And I think a lot of the progress has been made by realizing that there are a lot of things that you can understand about black hole physics without trying to necessarily reproduce the exact discrete spectrum of microstates in some model of gravity. So, for example, I think the original motivation for this might come from Cardy's formula, which is a universal formula obeyed by conformal field theories in 2 dimensions, which reproduces black hole entropy in terms of the asymptotic density of states of conformal field theory. But it's a density of states. It's not a discrete spectrum. And any individual conformal field theory, of course, will have a discrete spectrum, but it's only in some coarse-grained sense that Cardy's formula is reproducing that. So Cardy's formula is reproducing an approximate density of states at high energies, whereas any individual conformal field theory will give you an exact microscopic density of states. But I think what Schenker and friends sort of very, very clearly articulated is that you can go much farther than just talking about the density of states. You can talk about the statistics of microstates. So the density of states would be something like, some smeared version of the density rho of V of the number of states. But you could also talk about things like the 2-point function of the density of states, or the 3-point function of the density of states, or something like that, which would be some average or some smeared version of the square of the density of states, or the cube of the density of states. And so, for example, one of the things that I think really motivated this field is the recognition that there are gravitational saddle points that reproduce things like the 2-point function of the density of states. not just the 1-point function of the density of states. So for example, if you think of a black hole entropy as being described by, the semi-classical black hole entropy is going to be an average of a density of states at high energy. You could also look at the average of the 2-point function of the density of states, which is telling you not just about the density of states, but telling you about, for example, level repulsion between the density of states. And so, so for example, this is something that we encountered yesterday when we talked about this very simple Euclidean wormhole solution in 2 dimensions. We decided that the cylinder amplitude, so for example, in that very simple model of 2D gravity that I was starting to describe yesterday, we had a disk partition function, which is giving you the trace of e to the minus beta h, the averaged value in our interpretation. But you also had a cylinder amplitude that was telling you the variance of trace of e to the minus beta h. What is that? That's the 2-point function of the density of states. And that thing will encode level repulsion. Okay. So for example, a very famous feature of probably one of the defining features of chaotic systems is that they exhibit level repulsion. So if you have an integrable system, then typically the states of the system all pile one on top of one another because the states live in representations of some gigantic symmetry algebra. But on the other hand, if you have a chaotic system, then typically all of the energy eigenstates are non-degenerate, and they'll repel from one another. And so, for example, this wormhole amplitude is telling you about the statistics of the 2-point function of black hole microstates. And so I think one of the crucial insights is that even though you have a gravitational theory that might not reproduce the exact microphysics, that is to say, the exact discrete energy spectrum, nevertheless, you can still reproduce more refined features than just the density of states. And so, I think this JT gravity exhibits that very clearly. This U1 gravity related to the Noreenos ensemble exhibits a version of that. That is a system where you can even reproduce some of the microstructure, exact microphysics of these black hole states from a gravitational interpretation, although it's still an ensemble averaged theory. Okay. Good. There's a question, Upamanyu.
Yeah, thank you. If I understood correctly, earlier today in response to one of the questions, you had suggested that different members of the ensemble, ensemble of CFTs on which the probability distribution is defined, there could be different bulk duals for the different CFTs. So I was wondering whether it would be appropriate to say that the gravitational theory, which is dual to this ensemble of CFTs, is also dual to some ensemble of other gravitational theories, or is that a too vague statement?
I think that's inevitably what you're led to. We think of a simple gravitational theory as some average of many fancy gravitational theories. And that is, of course, it resonates with the sort of effective field theory approach, where you might have one low energy theory of physics with many different UV completions. And indeed, I think that's exactly the right point of view to take on this subject. I think the thing that I want to articulate clearly, though, which is different from the standard effective field theory approach, is that usually in effective field theory, you don't quantize, you don't study non-perturbative effects in effective field theory. You don't study, high order quantum effects in an effective field theory. But these are all sufficiently simple theories of gravity that you can actually sum up, a full series of non-perturbative effects and get, an exact, and match that with an ensemble average of CFTs. In the JT gravity example, you can compute all perturbative effects and all non-perturbative effects. And the theory is still missing what people call doubly non-perturbative effects in order to get an exact sort of UV complete theory, but you're almost there. And similarly, in this Narain theory, you know, when one studies the ensemble average of these free boson conformal field theories, you get something which is includes all perturbative effects and all non-perturbative effects of a theory of gravity. Now, it's a rather exotic kind of theory of gravity. It's not really a theory of metrics, or, you know, it's not, I think, best understood as a theory of metrics, but rather as, you know, something closer to a gauge theory. But still, it has many of the characteristics of a theory of gravity.
I have one related question. The different members of the ensemble of CFTs. What features, I mean, at least what features do they have or should they have absolutely in common? For example, should there, I mean, let's take ADS3 gravity, for example. Should their central charges lie between some particular range, or is there any restriction that forbids them from having two different, I mean, having some order of magnitude difference in these central charges? So I just want
nobody. The answer is nobody really knows. Okay, so if you ask me what I think is true, I think it is likely that three-dimensional pure gravity in ADS should be understood as an average over all two-dimensional conformal field theories. What I don't know is what the correct probability distribution on that space of theories is. Although I think, based on the analogy with, you know, some results, okay, I think there's some plausible guesses for what that measure is, but I don't think, for example, we know exactly how the coupling constant of the theory of gravity, which would be the Newton, you know, the ADS radius and Newton's constant, the dimensionless coupling, should map onto the central charge of the dual ensemble of CFTs. So the standard answer that you would guess based on the Brown-Hanot formula is that the central charge is related to the ADS and Planck unit, the ADS radius and Planck units. But I don't know that that is completely correct. I mean, I think it could also, that may be something that is true on effectively at large central charge in the semi-classical limit, but it's not obvious to me that it shouldn't be modified in some way. You know, so for example, I think it's perfectly plausible that the ADS radius in Planck units is not the central charge, but instead is something closer to, you know, a chemical potential conjugate to the central charge or something like that. That's something that shows up, for example, in symmetric product orbifolds and in some of the examples that we understand a bit better. Good.
Thank you.
Thank you. Sorry, that answer was getting into some technical stuff that we haven't really covered in the lectures yet.